Yeah, my name is Will Nesda. I'm a master's student working under Krista Haskey with the Subsurface Hydrophysics Group at UW-Madison. I work on understanding PFAS transport and fate within the unsaturated zone, also known as the vadose zone. And then in this presentation, I'll just be discussing a bit about how our group is investigating different adsorption mechanisms to create better unsaturated transport models. So tiny bit of background. I'm sure everybody has had a lot of PFAS background, but PFAS are a really hot topic these days. The emergence over the last few years has been pretty alarming. That map in the bottom kind of shows sampling efforts. It appears that the more we look for PFAS, just the more that we find. And recently in Wisconsin, northern Wisconsin, at Oneida Rhinelander Airport, um, some of the groundwater drinking wells hit PFAS concentrations above the EPA health advisory limit, causing the shutdown of several municipal wells. Now, if we were to zoom in on an area kind of around those wells above the water table, we would be within the vadose zone. And this is something that we might see in this kind of cartoon schematic. So it's a combination of air, water, sediment grains, and PFAS adsorbing to different interfaces in the vadose zone. So this combination of different phases and PFAS introduces considerable modeling complexity. Some PFAS adsorption behavior relates back to the hydrophobic and hydrophilic properties of the molecule, as we know. But over time, some dissolved PFAS in water will kind of seek out these boundaries between these fluid interfaces and solid interfaces. And once adsorbed, they're likely to stick around for a while. But the vadose zone is this incredibly dynamic system, and the spatial distribution of the fluids within the vadose zone is always changing due to events like big recharging events like rainfall and flooding. So one can imagine that over time, PFAS will kind of distribute across the vadose zone and be remobilized during large recharging events. The vadose zone is really this crucial boundary preventing a lot of contaminants from reaching groundwater. So but some studies have shown, though, that it can be a source of continuous leaching of PFAS into groundwater over long timescales. Kind of the aim of our research is to develop more mechanistic understandings of how PFAS distribute at these interfaces and how these dynamic conditions influence the mobility of PFAS throughout the vadose zone. We use a combination of a lot of empirical and theoretical approaches, which I'll describe in the slides. And hopefully in the end, we're going to have better PFAS risk and mitigation models. So now we can kind of dive into fun math. So the equations here describe the degree to which adsorption onto these different phases slows the transport of PFAS relative to advecting water. So this is denoted by the RAW and the RSP terms. RAW is related to air-water adsorption, which consists of KAW, the air-water adsorption coefficient, and AWI, the air-water interfacial area, which is normalized by the volumetric water content of the porous medium. And similarly, we have this RSP, which relates to the solid phase adsorption component by this KD term, which is the solid phase partitioning or adsorption component, and then we multiply this by the bulk density of the porous medium, and again, divide out by the volumetric water content. So these two adsorption mechanisms typically dominate in a lot of unsaturated systems. However, there are other mechanisms like partitioning into NAPLs and air-water partitioning as well. So now that we have some of the math, we actually have to go in and experimentally quantify a couple of these terms, especially the ones in bold. So first, for the solid phase aspect, to quantify KD, we use batch type experiments where we place some soil in contact with aqueous PFAS for a time, agitate those samples. After agitation, some PFAS will be stuck to the solid phase and the rest will be in the liquid phase. We take the liquid, send it through an LCMS, and then analyze that for whatever concentration is remaining in aqueous phase, which, if you watch the previous discussion, can be a little difficult with some current LCMS stuff. So I was really interested in a lot of what was going on in the previous talk, because I deal with all of those issues at low concentrations as well. So from this analysis, we can build these isotherms, the slope of which gives us that KD term. And PFAS at elevated concentrations have been shown to exhibit more like Freund-like behavior, kind of this exponential. But in the range that we're really concerned about, which is this low part per trillion, part per billion range, this linear isotherm can suffice, but it's not ideal. So now we go to this air-water side of stuff, of the transport modeling. To approximate that KAW term, we measure the surface tension using a tensiometer, this thing all the way on the left, at various PFAS aqueous concentrations, and then we fit an absorption model to the data points. So in this case, the plot in the middle is showing a Langmuir fit to the measured data that helps to extrapolate the PFAS absorption at the air-water boundary for very dilute and environmentally relevant concentrations, that part per billion, part per trillion range. And once we fit the data, or once we apply fits to the data, we can apply some fun adsorption theory and actually calculate KAW, as is shown by the rightmost plot. We find actually that using the assumption of the Langmuir isotherm, KAW remains constant under the range of interest. And now comes the really challenging part, which is quantifying this AWI term, or the air-water interfacial area, which is just the area between air and water within a porous medium. This is really important for relating KAW back to the porous medium. So typically at high water saturations, most of the pore space is filled with water, which decreases the relative amount of AWI because most of the water is occupied in the pores. Once we start to drain those pores, AWI increases up to some residual value. The behavior of AWI at low water saturations is extremely difficult to experimentally measure, so we have to rely on a lot of empirical models that relate capillary pressure, which is in blue, to some sediment properties, which is some of these terms in black, and then that gets related back to AWI in red. Different models can show a lot of different behavior at low saturations. There's linear models, there's exponential models, which is the one on this plot. There's some parabolic models where at really low saturations, you're actually really decreasing your air-water interfacial area. That gets into a whole big thing that I can discuss with anybody that wants to know it. But the main takeaway of this is that AWI is really important, but it's really difficult to measure. And eventually our lab is hoping to try to develop some methods to measure this. And so with that, we have the major pieces of the adsorption puzzle. We can lump those two adsorption mechanisms into one term, R, and then we can apply this equation to different PFAS species and in different environments. But there's one really complicating factor when we try to apply this, and that's heterogeneity. So when we try to apply all of our adsorption theory to field sites like the Oneida Rhinelander Airport, we are not accounting for the complexities of the subsurface. So typically transport models assume simplified homogeneous systems, which work really good for a lot of contaminants, but PFAS are really tricky because they love that air-water interface and they have different absorption potential to different components in soils. So on this leftmost plot, this is a lot of the data from the field. We took several borings at the airport field site to create this picture of how different sediments hold onto their water with depth in the vadose zone. So this helps us to understand how those air-water absorption mechanisms differ between different kinds of sediments and within the same boreholes of sediments. So when we constrain the range of these sediments to our coarse material, represented by this gravelly sand at the bottom, and our fine material, which we term as silty sand, we make those constraints, and then we can confirm those with kind of grain size distributions as well to get a good sense of sediment-wise heterogeneity. And we find, at least at this site, that the upper section often contains layers of silty and fine material that coarsens with depth. And then additionally, we have to look at the distribution of organic carbon, and we find that it's largely restricted to the top meter or so, but this helps us to understand more of that solid phase adsorption component because PFAS love to adsorb to organic molecules. So now we have a good sense of the bigger heterogeneity picture at our field site. and we can map out the full range of PFAS absorption in the vadose zone. So here's a kind of complicated figure, but I'll walk you through it. So here is plotted R in its full continuous range from the equations described earlier. And it's mapped across a representative slice of the vadose zone at various degrees of saturation. And in this example in particular, we're looking at PFOS at some initial concentration around 100 parts per trillion. And it takes directly from this leftmost plot, but now we're just mapping it onto the R space. So the first thing to note here is that the values for R are extremely high. You look at the color bar here, it's plotted in log space. And what this is saying is more or less PFAS, especially in this low water saturation zone, is pretty much immobile in the vadose zone, in the upper vadose zone. And with these plots, we can plot our different sediment types on the map, and we can gain a sense of where PFAS is going to be more mobile or nearly immobile. And something interesting that we find from this is that coarse material, like gravelly sands, at the bottom of this plot, show really high PFAS absorption at low water saturations, which is a little bit counterintuitive compared to fine material, which shows less absorption overall at low saturations. And this is largely due to that dominant influence of the AWI absorption or air-water absorption, which dominates over the solid phase absorption typically, unless you have really, really high organic carbon content. Fine material will typically hold on to more water, causing a decrease in the maximum value of air-water interfacial area and result in lower overall absorption. To a little bit more clearly demonstrate this, we can convert this map into a 2D space and see how this absorption changes with depth to the water table. You carry over that y-axis. It's the same on this plot.
3 minutes remaining.
Cool, thanks. So the profiles are really, really complex and very difficult to implement into transport models. So we actually apply a method of that averages the profile across the vadose zone thickness to give us one value for R. And we can use this. It has the added benefit of kind of constraining the adsorption that we can find, or the range of adsorption that we can find at a particular site, accounting for heterogeneity. And then we can also look at discrete borehole data and find a good average so that we don't have to try to model for all of these discrete points. And in the end, this kind of synthesizes this really complex retardation profile, or R profile, that we find in the vadose zone for PFAS. And then this leads directly into some future work that we're hoping to do when we take these kind of generalized vadose zone profiles and we can actually predict transport in heterogeneous systems. So we can constrain the adsorption heterogeneity by our profiles and field measurements, and then use some geostatistics to fill in all the gaps. So on this cube here, we can constrain some points and fill in the gaps of all of the heterogeneity across an entire site. And then in the future, we would like to implement some transient conditions, so like rainfall events, and just build really cool transport models that will hopefully give us a good estimate of the uncertainty in modeling PFAS in the vadose zone and help with risk mitigation and all that other fun stuff. And for right now, this is kind of a dream stuff that I'm working on, but it's really cool, really fun. So some major takeaways, just PFAS may be subject to periodic immobilization due to adsorption at the air, water, and solid phase interfaces. And this is explained by field observations of long-term leaching into groundwater, kind of displayed by this quote at the bottom. And then finally, that heterogeneity, as always, just introduces a ton of complexity into transport modeling. So I'd like to thank the NSF grant for sponsoring a lot of the funding that has gone into this, as well as our undergraduate lab technicians and field assistants and everybody that's been doing a lot of work to help with this project. If you're curious about more of the science that we do at the Subsurface Hydrophysics Lab, and there's a lot between bacteria transport, colloid transport, all this cool stuff, then there's a QR code here that will bring you right to the website. And with that, yeah, I'll take any questions.
Thanks very much. Well, that was really interesting. Unfortunately, we don't have time for questions.